We want to get an overview of precalculus, both as it relates to what's gone before and what comes after. So precalculus is a basis of mathematical analysis, and it has two roles. One role is as a foundation for later courses. Now, as a foundation, I mean a foundation for courses that don't really go beyond the level of precalculus, but which apply the concepts of precalculus in a modeling context. So many courses, for example, a non-calculus based statistics course, which is in the future of just about everybody who is going to go into any discipline that uses mathematics, and the majority of disciplines do. So we have the modeling aspect that's founded on a knowledge of precalculus. We also have the role of precalculus as a transition to higher level mathematics courses, the courses that build on precalculus and move on in deeper and deeper into the mathematics curriculum. So we have the transition to calculus because, of course, precalculus really kind of means something you take before you take calculus. It gives us the transition between high school math, which is based on geometry and algebra, and hopefully you have a good foundation in those courses. I think you wouldn't be in this course if you didn't. So we reinforce what is learned in those high school courses, and we move beyond it to a higher level of abstraction, to a more powerful picture of mathematics. And that works perfectly well as a foundation for other courses that don't really necessarily go beyond or don't go far beyond precalculus, and as a transition to the calculus. Now, we say it's a basis of mathematical analysis. I'm not going to detail what mathematical analysis constitutes or what constitutes mathematical analysis at this point. Just going to talk a little bit about precalculus, which consists of many ways to express what it consists of, but I'm going to say it consists of analytic geometry, matrices, and elementary functions. These are the main points of focus for a precalculus course. Analytic geometry starts with something as simple as the equation of a straight line and the distance formula, or the Pythagorean. I don't like to think of a distance formula personally. I like to think of the application of the Pythagorean theorem to triangles that can occur in a Cartesian plane, but that's a finer point that we don't need to discuss any further. We start with those fundamental ideas and move as far as the conic sections. Matrices start as usually in response to the problem of solving systems of linear equations, linear simultaneous equations, and move into the algebra of matrices to some level of depth. And matrix algebra then explodes into, in higher mathematics at the calculus level and beyond, into the idea of linear algebra, into the subject of linear algebra, and beyond that, abstract algebra. The foundation is obtained starting with the study of matrices, typically in a precalculus course. So we do the matrices, we do some matrix algebra, and we begin to understand the abstraction of a mathematical system, although we don't go into great depth with it. We get prepared for linear algebra course. Elementary functions, well, if there's one main focus of a precalculus course, it's in understanding elementary functions. The algebraic properties of elementary functions, their geometric properties, and real-world applications of the elementary functions. And the elementary functions basically consist of what? Linear functions, power functions, polynomials. And polynomials are, of course, built up as a sum of power series functions. So not everybody would call them elementary functions, but we have exponential functions, logarithmic functions, and the trigonometric functions. All these apply in the real world in some way that's likely to be important at some point in the study of just about any subject. With the elementary functions, we learn to construct the graphs of transformed and combined functions, transformed and combined elementary functions, which still come under the classification of elementary functions. The ones I listed are kind of the fundamental functions, the most basic functions, and all other functions are obtained by combinations of those functions through transformations and combinations by arithmetic composition and so forth. This leads to the idea of functions and function families as entities, which is kind of an abstract notion. Not too abstract. We can understand this, but this is one of the emphases of what I consider to be a complete precalculus course, and something that's really not well done in many precalculus courses. Hopefully it will be in this one. Okay, so we talk about, again, the context, foundations, and modeling. I've addressed that. We have the transition to calculus. The one big goal is to make calculus as easy and powerful as possible. Okay, we get the foundation for making calculus as easy and powerful as possible. This also provides us with a foundation for modeling in courses that don't really go beyond the level of precalculus. Okay, we have the idea of rate of change, slope, and difference quotient. These are, again, important concepts, important ideas, regardless whether you're moving to calculus or not. But they're absolutely essential in calculus. In calculus, the most fundamental notion of calculus, it could be argued, and many would agree, is the idea of rate of change and how that generalizes. And then we have sequences and series, which are, again, very important in themselves for understanding topics that don't go far beyond the level of precalculus, but also extraordinarily powerful in the context of calculus. And you really don't get to this till the end of a first-year calculus sequence, usually, the formal study of sequences and series, but we need to lay the foundation for that, and also a foundation for the use of sequences and series in courses that don't go far beyond the level of the precalculus. Now, we need to learn, in any case, wherever your future is in mathematics, we need to improve our ability, I say to learn. You've already learned to formulate problems to some extent in prerequisite courses. But we need to extend our ability to formulate problems, and we need to develop a bigger picture of the foundations and the idea of mathematical proof. Now, we don't go too deep into the formal idea of proof, but we do go as far as mathematical induction and the idea of proof. And in the more advanced problems that you'll have an opportunity to work on, you do get a good foundation for the idea of what it means to prove something in a mathematical context. And you're going to need that in calculus, and especially if you go beyond calculus. Okay, we need to learn to solve equations. There are a number of different types of equations. You've learned how to solve linear and quadratic equations and certain other types of equations in your algebra courses. We have, though, in precalculus, we encounter, if you haven't encountered it already, exponential equations, logarithmic equations, trigonometric equations. Okay? We need to know how to manipulate expressions and equations against something you already know something about, but we need to get a little better at it. We need to develop that as we grow mathematically so that we can apply it, whether in making the transition to calculus or in a modeling context or in some other context in courses that require only precalculus. Okay? So, we need to be able to rearrange expressions and equations for a purpose. Okay, now I can't tell you too much about what that is, except that an expression or equation is going to tell you more if it's in the right arrangement, if it's in the right configuration. So we need to learn how to achieve that. We have the trigonometry. Apart from trigonometric functions as an important subset of your elementary functions, a critical subset of your elementary functions, we also have the trigonometry that applies in the real world through the triangle trigonometry and the vectors. Triangle trigonometry is absolutely essential for most STEM areas, especially those that are very mathematical, such as physics, chemistry, and so forth, and vectors, which are, again, extraordinarily important in those areas. We also have the trigonometric identities that support the application in these areas, in the real-world applications, and in theoretical applications. So I can't say too much more about that right now, but we see the real-world elementary functions can be modeled in the real world to help us understand the real world. Modeling is generally done with real-world phenomena. All the trigonometry, especially the triangle trigonometry and the vectors, supported by trigonometric identities, applied directly in the real world. So we have kind of an overview of what we mean by precalculus and what we stand to learn in precalculus and where we're heading.